Hello, everybody. Welcome to the seminar. Today it is my pleasure to introduce you to Dr. Julie Wardlow, who will talk about her work on rare dusty galaxies identified by the Herschel Space Observatory. Julie did her PhD at Durham University in the UK, where she worked with iron snail and submillimeter galaxies, and in particular in the La Boca survey. She then moved to the University of California in the USA, where she worked with Asanta Curry on the Herschel telescopes Hermes and H-Atlas surveys. Since 2013, she has been a Dark Fellow at the Dark Cosmology Center at the University of Copenhagen in Denmark, and she has been working on the Herschel surveys and on lens galaxies as well. Thank you, Julie.
Thank you. And thank you for having me, and thank you for showing up. It's a great pleasure to be here. So I'm going to be talking about these rare dusty galaxies that we detect with Herschel in the wide field surveys. And I want to acknowledge my collaborators who are listed on the bottom there. In particular, Paloma and Rui and Ismail, who are here. And that's why I'm here this week, is to work with them and progress this work a bit further forward. So first I want to motivate the study. So we're looking at dusty galaxies at high redshift. And the reason for that is severalfold. So firstly, if you look at the high redshift universe, galaxies are very different then to what they are like today. So this is showing a fly-through of the Hubble UDF. So the beginning is showing local galaxies, redshift 0, and then as this movie progresses, we're going back in time, so we're going to higher redshifts. And you can see the galaxies change. They start off multicolored, lots of structure, and as you get to the higher redshifts, they become much bluer, they're more blobby, lots of less uniform systems. So the question is why? And we actually can't answer that question just by looking in the optical or just by looking in the near infrared. We need to go to the far infrared. And so that's what Herschel does. It goes into the far infrared. And one way to really emphasize this point is to look at the distribution of the cosmic background intensity as a function of wavelength. So the blue region on this plot is the optical and near infrared background. So the area under that curve is the intensity of the entire background at those wavelengths. And then the red region of this plot is the far infrared. And so you can see that the intensity, the total sum of each one of those is about the same. So this is telling us that if you go back through the whole history of the universe and you only look at the optical and the near infrared, you miss 50% of the light that's been emitted. Because 50% of the light that's been emitted is reprocessed through dust and then re-emitted in the far infrared. So we really want to study those wavelengths, otherwise we're missing half of the information that the universe is giving us. Another neat trick with the far infrared is the so-called negative K correction, which I'm just demonstrating here by showing the SED of ARC 220. So the purple line at the top is at redshift 0.1, and that's what the emission of ARC 220 looks like if it was right near us at redshift 0.1. But of course, as you redshift things, you have to move the entire wavelength distribution, so the whole SED shifts because of the redshift, but the whole thing also gets fainter because you're looking farther away. And so that's indicated by the different curves. So we go from redshift 0.1 to redshift 8. And you can see in the optical and near infrared, which is on the left here, the flux gets much fainter very, very quickly. So as soon as you start going to higher redshifts at those wavebands, galaxies get really faint really fast, and that makes them very hard to detect, and that makes them even harder to study. Whereas if you look in the submillimeter, or the far infrared, which is what I'm going to be talking about, which is the two gray bands in the middle, here, you can see that as you go to higher redshift, the flux that you receive actually doesn't change very much. So that means you can study high redshift sources very efficiently, because they're not that much fainter from local sources with the same luminosity. So you can see similar luminosity sources at high redshift without any extra effort on your part. So that's really useful. And then finally, you also need to study these sources because it's thought that they're an important phase in the evolution of galaxies. So, you know, high redshift, you might have spirals or disk-like galaxies. And on this slide, I don't try to read the text. This is just a schematic. So going from the isolated disk on the left up to the top and round and back down again to the dead elliptical is a proposed timeline for galaxy evolution, or a sequence for galaxy evolution. So it's thought that at very high redshifts you may have disks or isolated systems. Perhaps there's a merger, or maybe there's just disk instabilities that triggers a kind of starburst. And that's shown by the panel D, coalescence ULEG here. And that phase is enshrouded in dust. So if you look in the optical, you can't necessarily see that there's loads and loads of star formation going on there. But if you look in the far infrared, all that star formation lights it up really brightly. So you can see that there's some very active galaxy there. And this is the phase that we're targeting, this bright starburst phase. And then following on from that, the thought is that there's some kind of blowout where the dust is dispersed. And then you end up with an AGN and a quasar that eventually settles down into a local dead elliptical galaxy. And that's demonstrated here. So this top panel is showing, as a function of redshift, the dark matter halo mass of different galaxy populations. The red band is local elliptical galaxies, and then the dotted and dashed lines are showing the evolution of a halo. So if you have a halo at redshift 5 of about 10 to the 12 solar masses, it obviously gets bigger as you go to lower redshifts. And so it gets more massive as the systems evolve. So that mass increase is traced by these lines. So submillimeter galaxies, or these dusty ULEGs that I'm talking about, at redshift 2, they have halo masses indicated by that big purple cross. And that's coincident, that makes sense if they then evolve into these more massive local elliptical galaxies. So if you want to know where local ellipticals came from, you really need to figure out what happened to these in these submillimeter galaxies in these dusty ULEGs. The bottom panel is showing the same thing, but in addition to local ellipticals, we also observe small, compact red objects, and they don't seem to have much star formation going on at about redshift 2. Which is shown in the middle of this bottom panel. So if you trace those back in time, the thought is that they perhaps started off as a dusty star-forming galaxy at redshifts 4 and above. So in order to be compact and quiescent at redshift 2, they need to have gone through this big burst phase of star formation at redshift 4 and above. So we want to study these populations. And I'm going to demonstrate to you 2 techniques to do that. The first is using gravitational lensing, and that will show us the populations at about redshift 2, but there's some distribution on that. And then the second is how we can select these really high redshift systems, redshift 4 and above, using just Herschel data. So first off, a quick primer on gravitational lensing. So you might be used to seeing this kind of picture where you have in the middle a cluster of galaxies that's between our telescopes on or around Earth and a distant galaxy. And the light gets magnified by that cluster, it gets distorted by that cluster. But actually, I'm not going to use clusters, I'm going to use single galaxies. And the same effect happens. The light is magnified and distorted by the foreground galaxy. And I'll refer to the foregrounds as the lensing galaxy, or the foreground galaxy, and then the background SMG, I'll refer to as the background galaxy or the lensed galaxy. And the reason we do this is because you get a flux boost. So something that would have appeared faint without lensing appears much brighter. And you also get a spatial resolution boost. So you can see the detail of the systems, even though they're at high redshift. And if they weren't magnified, it would be very hard to disentangle the different features. You can do that using lensing because it magnifies spatially as well as in flux. And you can also study the foreground mass profiles of these galaxies, of the foreground galaxies. So you can study the entire mass, not just the stellar mass. So you can effectively trace dark matter in those systems. And then finally, the number of lenses and the distribution of them tells you about, can tell you about cosmology if you know where they are. So I'll just demonstrate those 3 points with a couple of examples. This is an H-Atlas galaxy. So this was discovered in one of the Herschel surveys. And then we went and we followed it up with almost as many telescopes as we could get our hands on. The left-hand panel here is showing what we see in the sky. So this is observed. And the faint red arcs in that are the background galaxy. So that's the lens system as it appears to our telescopes. And the foreground systems are labeled G1 to G4. So they're doing the lensing. They're deflecting that light. So if you trace this back and you say, okay, that's what it looks like as we see it, but what did it look like in the source plane? If this lens wasn't there, you get the right-hand panel. And you can see from that the gray and the red contours are the distribution of stars that we think of there in that system. So it's very non-uniform. In fact, it's probably a merging system, two galaxies colliding. But then if you trace the gas, and we do that through CO observations, the gas appears to be in that big green region. So the gas is much more distributed, much more extended, and it's offset from the stars. And the dust is offset again, but is much more compact than the gas. So these three components of the galaxy have been moved around by this merger. And we wouldn't have been able to see this much detail without the lensing. You couldn't disentangle that without the lensing because of this spatial resolution boost. Okay, so the other thing I said you could do is look at the foreground masses, the foreground galaxies. So there's just two examples here. So first off, if you know, you can measure the stellar mass of the galaxy fairly easily of the foreground system. And then you can use the shape and the positions of the arcs of the lensing galaxy to calculate the total mass that's enclosed by that arc. And that's what's shown in the left here. So this is stellar mass as a function of, stellar mass on the x-axis, and then the y-axis is the fraction of that mass that is stellar. So you can see that for the galaxies in this survey, about 50% of the mass, about 50% of the mass is actually dark matter, and 50% of it is stellar. But you can go one step further. If you get lucky and you have two background galaxies behind one lens, which is shown on the right, you get these multiple arcs. So then you have a measure of the total mass at two different positions. And so then you can trace the profile of the mass, and that's shown in the bottom right, where the blue curves are the light, so that's the baryons, that's the stellar mass. And the red points is what you infer as the total mass from lensing. So you can see here the difference between those sets is the component of dark matter. And then you can look at the statistics. Rather than just looking at individual systems, look at the statistics of the distribution of these systems. So this is a result from the SDSS quasar lens survey. And on the left-hand side at the top is the distribution of angular separations between the foreground source and the background arc. And then the different curves show what happens if you change the cosmology. So if you know your selection function very well, you can say which of these cosmologies best matches my distribution of angular scales. And similarly, you can look at the redshift distribution of the foreground lenses, again, if you know your selection function very well, and compare that with what you would expect from different cosmologies. And that's exactly what they did to get the figure on the right. And that's showing the mass density and the dark energy density. And the curves here are from the lensing. So the red region shows you what happens if you do the statistics for the SDSS quasar lens survey. And that constrains the cosmology in that region. And you can compare that then with the result that you get from baryon acoustic oscillations or from studying the CMB with WMAP. So you can see that the angle of this is very complementary to those other studies. So it's a different way of getting at the same question. So I'm going to address these things using mostly the data from the Hermes survey. So this is just a quick summary of Hermes. It was a survey with Herschel, and almost all of this data is now public at the website at the top there. So you can go download the catalogs or the maps from that website. And it's a survey that's wedding cake in structure. So there's some very small fields that we went very deep, and then there's some wider fields where we went shallow. So you can get good statistics in different regimes from this survey. And this is what the data looks like. So this is a really small fraction of the imaging. This is less than an arc minute, less than a square degree. The whole survey is about 380 square degrees. So this is a really tiny fraction. But the things to take away from this is that every bump and wiggle on that map is a galaxy. Every single thing in that image is a galaxy. There's no real background in here. It's all sources. And then you can see from this that the sources are different colors. There's very obviously red sources. There's very obviously blue sources. And they're different luminosities. So you can see the brightness very clearly. And we use those two techniques to pick out the interesting sources, these rare galaxies, say the very, very high redshift ones or the lensed ones. So to find the highest redshift ones, we use the colors. This is the figure I showed you earlier. But now, instead of looking at the whole thing and saying, okay, submillimeter is great because you don't get this so much dimming as you do in the optical and the near infrared, I just want to zoom in that far infrared region. And so you can see here now the 3 Herschel Spire, which is one of the instrument's filters, are shown in with these dashed lines, and then the longest wavelength one is Laboca or Scuba 2. But what to really take away from this is if you look at the low redshift curves on there, the colors are blue. If you looked in the Herschel survey, a redshift 0.1 galaxy, you would see a blue source. But if you look at the very high redshift ones, say the redshift 8 curve, you'd see a very red source. So just by looking at the colors, we can extract the systems that we think are the highest redshifts. And that's exactly what we did. So this is now showing sources from Hermes on a color plot. So the x-axis is the 350 over 250 micron color. So as you go further to the right, you get redder. And the y-axis is the 500 micron over 350 micron color. And as you get further to the top, you get redder. So we selected the sources that are within that dashed region. And we said, okay, we think these sources are very red. We think they're probably at high redshift. So all the black points on there are systems that we selected. And we said, these are interesting. We're going to follow these up. And the red points are the ones that we followed up and we successfully got redshifts for. And their redshifts are shown on there. So you can see that all of these are very high redshifts. They're all there's one at redshift 3.3, and all the others are redshift greater than 4. And the one I'm going to show you in detail is FLS3, which is this one. This is a redshift 6.3. So this is the highest redshift submillimeter galaxy. This is the dusty star-forming galaxy, just a few million years after the Big Bang. But because it's bright and because it's found in Herschel, we could follow it up with a bunch of different telescopes. And this is some of the spectroscopy. This isn't even all of the spectroscopy. This is some of the spectroscopy we got in the far infrared. So we've detected CO lines, various different transitions. We've detected water. We detected carbon. We detected oxygen. So we know this redshift, there's no question. But we can use all this information as well to figure out what's going on in the ISM of this galaxy. So what's happening in the gas. And we can also calculate its basic properties. So it seems to be very luminous. About 3 times 10 to the 13 solar luminosities is coming out in the far infrared. That correlates to a star formation rate of about 3,000 solar masses per year. So that's 3,000 times more stars are being formed per year than probably the Milky Way on average. It's fairly massive, stellar mass of 4 10 to the 10 solar masses. So it's built up all that mass in just a couple 100 million years. The gas mass is also high. In fact, there's more gas than there is stellar mass, 10 to the 11 solar masses. There's a lot of dust, about 10 to the 9 solar masses, and a lot of carbon. So it's creating metals. It's made a lot of metals at this very early time. So like I said, you can use these lines to investigate the gas and the properties of the gas. So the figure on the left here is showing the CO excitation. So this is essentially, for each CO transition, how bright is it? And by fitting this, you can infer whether there's high ionization gas, whether there's the temperature of the gas. And we find that this is reasonably warm gas, about 140 Kelvin. And it's very dense. So it's similar density to local ULUX. We can play the same trick with the water, and that's shown in the bottom. And when you do this with the water, you find that all that water emission can't just come from collisional excitations. It has to be radiatively pumped. So to make those lines, you need some extra energy going in there. But you might want to know what this system actually looks like. So that's shown here. So the background image now is HST and Keck. So this is optical and near infrared. And then the contours on top are 1.1 millimeter. So the background is showing stellar light, and the contours are showing dust. So the contours is what we detected in Herschel, that kind of emission from the same regime. So of course we looked at this and we said, great, we've detected our galaxy in the optical and in the near infrared. So then we put a slit down, and we looked at the spectra with Keck Elris. And it turns out that at this position, there's a redshift 2.2 source. So we went back and we looked at it again, and we said, okay, rather than there being maybe a small offset between the optical and the near infrared, we think that G1 and G2, which are on there, the detected near infrared sources, are actually in the foreground, and they're a redshift 2. So there's probably some gravitational lensing going on here. So we did some lens modeling, which is shown on the left. So the leftmost panel, the contours is the data in the 1.1 millimeter, and then the background is what the model looks like. And then the blue points, if you can see them, they're what we think this source looks like in the source plane. So there's probably two components to this galaxy. And if you run through all the different combinations of error parameters and whatnot, you get the probability distributions that are on the right. And if you use one component in the background versus two components, you get slightly different answers, but not too much. So this system at redshift 6.3 is magnified by about a factor of 2. So all those numbers I gave you earlier need to go down by about a factor of 2. So this is kind of nice. So now we're using magnification to see the very, very highest redshift dusty galaxies. But we can also say, well, what are the statistics of these systems? So we looked in the two biggest Hermes fields and said, how many do we find? And it's actually quite a complicated question to ask, because you have a lot of uncertainties in how you extract the sources from the maps, how you calculate the colors and fold in the completeness and those kinds of factors. So these two histograms are the probability distributions of the number density for each of those fields. So it looks like we have a few per square degree of these red sources. And if you look at models, so now rather than just plotting, I'm plotting one data point, which is how many we find in Hermes. And this x-axis is a function, is a redness parameter now. And then the curves are different models. These are Betterman et al. Models, assuming different redshift cutoffs. So if you say all of these sources are at redshift greater than 5, and we use his 2012 models, you get that green line. If you say they're all at redshift greater than 4, you get the yellow line. And you can do this with different surveys and different models. So that's what we've shown here. So the circled numbers are for the survey. So those are what we detected. So just red sources, we get about 3 per square degree. If you say they have to be red and above redshift 3, we get 1.7 per square degree. And if you say they're red and above redshift 4, we get about 2.4 per square degree. And you can compare that then with the different models. And in fact, none of these models can reproduce the number of red sources that we find at high redshifts. So there's too many. It's hard to explain in simulations because you have to produce this dust very, very early, and that's hard to do. So I'm going to take a break from the red sources at ultra high redshift now and go back to lensing. So these are using what we know about lower redshift systems. I mean, the different models do it in different ways, but generally what we know about lower redshift systems and saying, okay, if there's star formation at a certain rate with a certain SED at higher redshift, what would it look like? So how many, if you evolve the model, no, these ones are not. These are more using the priors that we have from lower redshifts and evolving them as what you would perhaps expect. And that's why there's different numbers, because the evolution is different in different systems. I think it is, but we haven't done a high fidelity correlation. So everything I've seen so far, it's in conflict. And again, it comes back to it's hard to produce the dust so early. So it's in conflict as far as I'm aware, but we don't have the proper comparison yet. It's something we're working on. Yeah. So yes, the lenses. So we found a bunch of red sources, but now let's look at lenses, because those systems, you can get more detail. So how would we find lenses in Herschel data? It's actually very straightforward. So this is a plot of the number density of submillimeter galaxies. So this is actually at 850 microns, but the difference is small. It doesn't really matter for our purposes. And what you see here is that very, very faint sources are very numerous in the far infrared, but intrinsically very, very bright sources are incredibly rare. So if you look at the y-axis here, it cuts off at 1 per square degree. So this is cutting off below the number density of those red sources. But this was all done before Herschel. So this was in the limit of where you could only study fairly small fields in one go. When we went and looked at this with Herschel, you have a much wider area, which means you can find much rarer sources. And this is what we found. So when you get to the highest luminosities, the highest fluxes, you get this kick at the bright end. And this is extra sources that we weren't expecting to be there. So if you put a cut down, let's say 100 millijanskeys at 500 microns, you can select all those sources, and it turns out about half of them are local spiral galaxies. And these are things that you can see very easily in SDSS. They look like those images. You can see them mostly in 2DS as well, in DSS as well. So they're easy to remove. And once you've removed those, the remainder are our lens candidates. And we find about 0.15 per square degree. So essentially all you have to do to find lens galaxies in wide Herschel surveys is put a flux cut down and say, remove all the local things, and remove the blazars. And again, they're found in shallow radio surveys. And one nice factor about lens submillimeter galaxies is that you have this distinction between the foreground and the background galaxies. So now I'm showing SEDs again. So this is the flux that you receive as a function of wavelength. And if you have a starburst at about redshift 2.5, which is where most of these lenses are, you get the red line. So in the far infrared, it's extremely bright. In the optical and the UV, it's very faint. But the foreground lens has the opposite properties. The foreground lens is about redshift 0.5, and we usually think that they're early types. So that's shown by the blue line. And this is not numerically 100%, but it's an approximation for the average system. So a redshift 0.5 early type galaxy appears like the blue line. So in the optical and near infrared, that's very bright. But in the far infrared, it's very faint. So you can disentangle the two systems. You don't need to spend a lot of time trying to decouple your images because they naturally decouple on their own. If you look at far infrared, you see just the background galaxy. If you look in the optical, you see just the foreground galaxy. So you can separate them easily. And to give you a bit of an idea of that, this is one corner of the Hermes booties image. So this is the far infrared image. You have all the different colored sources, as we saw before. And there's one in there that's special, and it's bright, and it's fairly red, which is this one. So we zoom in a bit. The circle is about 60 arc seconds. And so you can see it kind of stands out very obviously from everything around it. If you then look at that with the SMA, which gets you very high resolution in the submillimeter, you see this. So you see this nice little ring, an arc, and that's a classic lensing configuration. And in fact, we followed up a lot of these. So now the right is showing SMA images for a large sample of them, and the left is showing it if you look in the near infrared with Keck or with HST. So in loads of these, you can see these arcs. You can see the rings. And so you can see that, I hope I'm convincing you that a lot of these systems are in fact lensed. So this simple selection of just a flux cut and remove the foreground, the local spiral galaxies, gets you lens sources. And if you look in ALMA, the same thing. So this is now ALMA data, so it's even higher resolution. And you can see again these arcs and multiple components. So we said, great, we can find lens galaxies, but let's try to model them. So now we did a basic model of trying to figure out how many we should find versus how many we did find. So the components are listed at the top. So we used a lambda CDM cosmology. We put down foreground masses with an NFW or an SIS profile, and we distributed them according to Schaffen-Tormann distribution. And then we took the redshift distribution of SMGs from Beckerman et al. And then we said, okay, using those components, we can calculate the probability, or rather, we can calculate the fraction of the sky that is gravitationally lensed by a factor of 2 or greater. And then you can use that to calculate a lensing probability on this number counts curve. And so if you assume the shape of the number counts as a Schechter function, so that's the gray band in the figure, and then minimize over the observed total number count, you can make a prediction for how many submillimeter lens sources you see. So the prediction of the number of lens galaxies is the blue region. So that's showing the uncertainties as well. That's why I shaded. And the data points, how many we did find, is the red points. So they're in very good agreement based on just the prediction. So then we can use this model to make other predictions about the properties of these galaxies. So we can look at the fidelity, for instance. So as a function of 500 micron flux, so if you cut at 100 millijanskis and say we want everything brighter than that, or if you cut at 80 millijanskis, we want everything brighter than that, this is showing you the lensed fraction once you've removed those local spirals and blazars. And when this paper was published in early 2003, the observed number was the red arrow there, so that was the lower limit. Now we've got more data, so we've updated these, so it's a little lower, but it's still within the uncertainties. So that's good. So this is really a high fidelity way of selecting gravitationally lensed systems. So then you can again use the model to say what's the mean magnification of these galaxies. So if we observe them with a given flux, perhaps what did they look like before? So this is the mean magnification. So if you observe it with 100 millijanskis at 500 microns, the mean magnification is about a factor of 7. And then it increases as your observed flux is higher. And you can fold that back in and say, okay, intrinsically, how bright were they? That's the solid line on this plot, and this is a probability distribution. So the majority of sources probably started off at less than about 10 millijanskis. And the red line here is showing the nominal Hermes detection limit. So if you didn't have lenses, you wouldn't be able to detect anything below that red line. So this model is suggesting that we're seeing sources that would be below the detection limit. But of course, we have this extra data, so we have extra components. So one of them we have is this is some examples from the SMA. So this is that high-resolution submillimeter imaging. And you can use this to lens model them. So that's what I'm showing here. The red and the grayscale are the image, so that's what we observe, and the model. And then the purple points in the middle is what you find in the source plane. So if you subtract the model from the observed data, you get residuals like this. So you can use these lens models of individual systems to calculate things like how magnified is this system? What was the size of the original source in this system? So this is the magnification distribution of the Hermes, and now this is including H-Atlas sources, which is another Herschel survey. They're selected in the same way. The red data points are what we observe. So if you do that lens modeling on the submillimeter array data, you get the red data points. And the blue dashed line is the prediction from our model. That's what I showed you earlier. So actually, we're finding that these are not as highly magnified as we predicted. So then we went and we folded in these data points into that model. And we said we use the data points as a prior on the model in addition to what we had before. And you get the purple line. And this is mostly changing because of the shape of the number counts. So the shape of the Schechter function has to change to do this. We also can look at the lenses, the foreground galaxies in those systems. So on the left here, I'm showing the observed I-band magnitude, and then as a function that's plotted against the Einstein radius, the Einstein angle of the lens. So that's how big the lens is. And so these systems are fainter than most others. So the big red points are our data from the submillimeter surveys, and the other data points are from other surveys. So we're finding fainter systems. And then if you look at the right, this is the x-axis is now the redshift of the foreground lens. So we're finding fainter systems that are at higher redshift than other surveys. So this is going to give us then an insight into the masses and the distributions of these foreground lenses in a different regime to what is studied by other lensing surveys. So we're finding a different kind of foreground galaxy. So you can learn more about the universe in that regime as well. I mentioned earlier we had HST and Keck data. So this is in the near-infrared. So we also did lens modeling in the near-infrared, and this was done entirely separately from the submillimeter lens modeling. So now you can learn about those two components differently. So this is just some examples of the near-infrared modeling. Now this time you have a foreground galaxy is detected as well. So you have to subtract that. And then we use the green regions that are encircled as the comparison region, so where we minimize the model. So now the third panel, the third line there, is the model fit. So that's what the model looks like. the blue data points are the source plane, and the gray is what it looks like in the image plane, so that's what we would see. And again, the residuals. So we can use that data and then say, for the same systems, what does the near-infrared look like versus the submillimeter? So now we're looking at the stellar emission versus the dust emission. And this is the magnifications for the two components. So the x-axis is now the submillimeter, and the y-axis is the near-infrared. And that dotted line is 1:1. So if the emission was coming from the same region in both wavelengths, you would be sitting on that dotted line. And most of these sources are not sitting on that dotted line. Most of them are sitting below. So they're more highly magnified in the submillimeter than they are in the near-infrared. And that actually correlates with the size of the source, the size of the galaxy. So this is the effective radii in the submillimeter on the x-axis and the near-infrared on the y-axis. So again, this is dust versus stellar emission. And they appear to be smaller. So most of these systems, the dust emission is coming from a smaller region than the near-infrared. So the dust versus the stellar is offset again, and there's different sizes. And then you can look at the magnification as a function of the near-infrared size. And now this is just for the near-infrared, so this is just the stellar region. And this is where some studies before have looked at this directly in unlensed submillimeter galaxies. And they come up with that gray region. The gray band is where other surveys have found sources. But they're limited by not being able to resolve really, really small things because they don't have the magnification to help them. So the systems that we're detecting in the red data points are generally coming up smaller in the near-infrared than studies that have been done before. And it's just because they didn't have that boost from magnification, so they couldn't resolve everything. If we look at the redshift as a function of the rest frame B-band magnitude now, so this is a pseudo-proxy for stellar mass. You can see the red sources there are our galaxy, so they're lens. And then the colored points are normal, dusty, star-forming galaxies. So they're coming up, they're similar to the normal galaxies, the normal star-forming galaxies, normal SMGs. But they're maybe on the faint end. So we can use this to then say, well, what we're probing here looks like to be the faint end of the normal submillimeter galaxy distribution, but we can see it in so much better detail than previously. So now I just want to link all this back together. We've talked about the highest redshift galaxies. We've talked about using lensing to magnify everything and get much better detail than what we previously had. So then we can look at the colors of the lensed galaxies. So the top plot is the 350 over 500 micron color as a function of 500 micron flux. The blue data points are the things that we selected as being very bright, but actually they're foreground spiral galaxies. Their redshift less than 0.1 or so. The red data points are the things that we think are gravitationally lensed. So you can see that the lens sources are on average redder than the spirals. That's what you would expect. And then we can plot this in the we can plot this in two-color panel as well. So 250 over 350 micron flux against 350 over 500 micron flux. And this is almost what I showed you earlier as to how we were selecting the red sources, the highest redshift ones. Only the axes are flipped. So now bluer is at the top and bluer is on the right. But you can say, okay, before we were looking at things that were actually red. So they were below the dashed line on the top panel and below the dashed line and to the left of the other dashed line on the bottom panel. And actually we find some very bright sources in that region. So we think these are lensed galaxies that are at redshifts greater than 4 or so. So we said, okay, we've got to follow these guys up. We can get both advantages here. We can study the highest redshift universe, the dust formation at the very, very highest redshifts, and we get this boost from magnification. And actually there's 4 of them so far that we have redshifts for, and I also have a Hubble program, and there's GTC data on all of these as well. So just a quick preview of what we're getting. This is 3 of the 4. These are all spectroscopically confirmed at those redshifts. And there's a very wide variety of morphologies, as you can see. So we have one system at redshift 5 that's probably lensed. It looks like there's arcs in the submillimeter and the radio, which is shown by the contours. And the other 2 are much harder to figure out what's going on, whether what we're detecting is a foreground system, whether the near-infrared, which is the background image here, is showing some stellar emission of the submillimeter galaxy, So that's one of the reasons I'm here this week, is to work on this problem and figure out exactly what's going on in these systems. So I'll wrap up here and just summarize. So firstly, I've showed you that you can very effectively select gravitationally lensed galaxies in wide field submillimeter surveys. And all you need to do is look at bright sources and then remove low redshift, very local spiral. And I've showed you how we're using those galaxies to study dust and submillimeter emission at redshift 2 to 3, and how we're disentangling what's going on in these foreground and background galaxies and really studying the physics in those systems. And then I also showed you how we can use submillimeter colors to identify very, very high redshift dusty systems. And in fact, the number of these systems is proving challenging for different models. So we're selecting sources that are going to tell us a lot about the universe. And these are subject of large follow-up programs, including some that are led here. So I'll stop there. Thank you.
Thank you, Julie, for this very interesting talk. Is there any question?
Congratulations. Very nice. I have two questions. One concerns the submillimeter sources. You have mentioned that you have been able to find smaller, fainter systems than the one known before.
Yes.
All right. Do you have any result out of this larger sample? For instance, concerning the most amazing number, which is the star formation rate. I mean, these submillimeter targets were very amazing because they hide a number of stars produced per unit time. So this new population of targets, which are not so big or not so bright, behaves the same? That's one question. And the second has to do with your lenses, which I know nothing about lenses. So did I understand well that in the previous slide that you showed, these are the one with the picture? Sorry, go ahead. Yeah, that you showed that one. So what you are saying is that these are peculiar lenses, and they look like things which are very irregular, very different, as you said. If that would be the case, all the numbers that you do to retrieve the information from these lenses are still all right? I mean, it is the same to have an elliptical galaxy or a cluster of galaxies being the lensing system as having something which is more amorphous, more gaseous, more whatever. I mean, the theory of using the lenses to get the information from the background source is still the same?
Yeah, so I'll start with the second question. So the lensing, it just depends on the mass. So it doesn't really matter if there's more gas or not. It's just the total mass in that system, in the foreground, that matters to how much is lensed. So with these ones, what we're still working out is whether the data that we're seeing in the near infrared, so the black points here, whether that is part of a foreground galaxy that is doing lensing, in which case it doesn't matter that it looks a bit different to normal, local lenses. It just matters that there's a lot of mass there. Or whether this is in fact background galaxies that are unlensed and then they're really, really bright and forming stars at rates that we just can't really comprehend. So that's something we're trying to figure out. But for the lensing, it doesn't really make any difference. Then the first question about the lens submillimeter galaxies and their star formation rates. So the answer is really in one of the slides I showed you, and it was a little hidden. So this is from the model, and I showed you it changes a little bit, but the gist is going to be the same. So this bottom panel shows you the intrinsic flux, and in the submillimeter, the flux is a proxy for the luminosity because you have this negative K correction. And the luminosity is a proxy for the star formation rate. So this is essentially a proxy for star formation rate. So the normal submillimeter galaxies that we detect with Hermes are above the red line. So they're slightly brighter than the bulk of what we're detecting here. So these things have star formation rates of hundreds of solar masses per year, rather than 1,000 or so. So they're still very, very bright and very active, but not quite so much as the others. but there's a lot of variation in the population.
Do you have an idea of the metallicity of these dusty, high-redshift objects start forming?
It's a hard question. Not a good idea. We think they're reasonably metal-rich, but there's a factor of 10 probably uncertainty on anything I could tell you. So.
Because if they are the progenitors of the ellipticals, of the local ellipticals, they have to be metal-rich already.
Yeah. So it's very hard to observe metal lines because they're so faint in the optical. It's very, very hard observations to do. Everything that we've seen so far doesn't contradict that they're probably metal-rich, but it's really hard to measure. So I'm not confident in answering positively in either way on that one.
Okay.
I'd like to comment, even Julie hasn't shown data, more recent data coming from ALMA, but we have several approved programs in this cycle of ALMA that's about to finish on these sources, one of them on spectroscopy, the other one on continuum imaging, and it's impressively quick how you can get redshifts for these sources. So in next talk, we will talk about those sources, but in a couple of hours with ALMA, you can get redshifts of sources of redshift higher than 5 very, very, very easily. I mean, if you select in this way.
Absolutely. ALMA is very good at doing this.
Is there any other question?
It's about the origin of the dust. Could you comment on that? It's produced in the starburst. It was already there, and you're seeing kind of screen through the...
Again, a hard question. A good question, but a hard question. What we're seeing is that the dust is often offset from the stellar emission, and we think that the dust is enshrouding the star-forming region. So if there's a burst in one part of the galaxy, it's not necessarily in the other part of the galaxy. So the light we see in different regimes is not always coming from the same region. So the general feeling is that the dust is being produced in the starburst, but it's difficult again to measure.
Yeah, so regarding, coming back to the point of the very extremely high star formation review you find, that it's more a comment. I mean, within a very basic, modeling, chemical evolution modeling, all what you need is something like maybe a factor of, 100 at most, or maybe if you want 200 solar masses per year to get the metallicity in solar metallicity, in just in a bit of time. Okay, so the fractions you are determining that would really push toward even higher redshift, the even older times, the bulk of the stars that we see today. So, I mean, the implications of this finding is extremely, something that, maybe change a bit the paradigm, and what we know.
Yeah, so we need to figure out exactly how many of them there are and exactly when they are. But yeah, I mean, we're certainly seeing a non-negligible number of bursty, high star formation rate galaxies at high redshift.
So this trick of using the color to simultaneously tell you about what the galaxy is like and also where it is incredibly elegant. But I sort of feel that, like many elegant things, there's this flashing orange light that it's too good to be true. And I think it isn't, but what aspect of it most worries you? You sort of, wake up in the night and think, oh crikey, what if that's not at redshift 6, but it's at redshift 4, but is it slightly, has a different spectrum? Which is the one that we should all be most aware of, most wary of, do you think?
The first thing to note is that whilst there's a flashing orange light, a large number of these we followed up and we have multiple line spectroscopy of. So we know for sure the redshifts of a bunch of them are at 4 degrees. When you're looking at the whole population and the statistics before you have spectroscopy, the biggest issue is the color variation. So there's some intrinsic color variation in these sources. So the temperature of the dust basically tells you where the intrinsic peak of that SED is. So if you have a cooler galaxy at a lower redshift, it will appear to be red. And I actually have a slide to show you that, because I sort of anticipated this question. Yeah. So this is from Alex Pope's work in 2010. So this was pre-Herschel. So the data points on here are all just a simulation. So they're saying, okay, if we assume some variation in the intrinsic SEDs of the galaxies, what would they look like? So this is now only showing 350 over 500 micron color as a function of redshift. So if you say we want things above redshift 4, that's where the dashed line is, the vertical one. And if you say we'll select the red sources just in this one color axis, and bear in mind that we actually use 2 for this selection, so we have an extra constraint, but you would select things above the dotted line. So you'd select some systems that are cooler, but at lower redshifts than what we hope. But the problem with this is that, again, all the data points on here, this is a simulation, and this simulation doesn't account for the fact that if you have very cool dust, for a given luminosity, there's more dust mass. So if you have very, very cool dust at lower redshift, so say this was something at redshift 2 masquerading as something at redshift 5, the dust mass in that system would be so huge, it would be almost unphysical. Or, to put it in another way, even if some of these are at redshift 2, they're still really, really interesting because they have a huge amount of dust that's just not been predicted at all. So we're either, most of the ones we followed up, we've proven that they're at high redshift with spectroscopy. If we find some that are at lower redshift, they're interesting in their own right for a whole bunch of different reasons.
Any other questions? No? So we can continue discussing in the scientific coffee at the library. And please, let's thank Julie again.